Well, good morning. The first thing I want to do with you is actually solve this challenge problem, which is on the PowerPoint we have been following. So example 13. During a challenging question, a student writes the following equations relating displacement S, velocity V, acceleration A, and time t of a car that speeds up from rest with constant acceleration. And then they come up with several equations, and the final conclusion of this student is that 2 equals 1. I will ask you to pause the video now, try to solve the problem, discuss with your friends in class, and then watch my solution. Okay, so here we are, and I'm going to be ready now to write the solution for this problem. So let's start with this here. U equals 0. Let's remember that U stands for initial speed, and since the object starts from rest, that initial speed perfectly is 0. Equation number 1 comes from S equals ut plus 1/2 at squared, and if U is 0, then S equals 1/2 of at squared. So equation 1 checks. Now he's going to solve for the acceleration. So basically he's going to multiply both sides by 2. So 2s equals at squared, and then divide both sides by t squared. And then we get a equals 2s over t squared. So equation number 2 also checks. Equation 3 is coming from v equals u plus at, where u is 0 and he solves for a. So a equals v over t. So equation 3 also checks. And equation 4 is basically just combining equations 2 with equation 3, and both check. Okay, equation 5 is just simplifying t squared. So equation 4 also checks, and equation 5 is also okay. Now, when he does equation number 6, S equals Vt. S equals Vt is an equation that comes from constant velocity motion. But this problem is not a constant velocity motion problem because it has acceleration. So here is my problem. Equation 6 cannot be used in here now because I have acceleration. If you guys finish the analysis, all of the algebra is correct from that point on. So it's a physics mistake, and the mistake is to use the constant velocity equation in a constant acceleration motion. Well, once we finish that last problem, which was numbered as example 13, moving forward, we're going to have example 6. A particle moves according to the following equation of motion: x equals 6 minus 5t plus t squared, where x is given in meters and t is given in seconds. And then you have several questions being asked. I will ask you to right now pause the video and try to solve the problem on your own before checking my solution. So for my solution on the problem, let's start with the general equation x equals 6 minus 5t plus t squared. So x equals 6 minus 5t plus t squared. Let's write down the general equation of constant acceleration motion, which is x equals x naught plus ut plus 1/2 of a t squared. Notice that this equation is not on the standard IB format. The standard IB format is basically S equals ut plus 1/2 at squared. Okay? But for this problem here, I need the equation in non-IB standard format. So to answer part A, the initial position, which is a starting point, I just compare the two equations, and that initial position is going to be 6 meters. To answer part B, the initial velocity u is going to be the coefficient of t, and that is -5 meters per second. And at transport c, the coefficient of t squared, 1, equals half of the acceleration. So the acceleration itself is going to be 2 meters per second squared. Oops, meters per second squared. Let me also rewrite this here in standard IB format. Okay? So if by any chance, as you are trying to solve a problem on your own, you got these three things wrong, then you're going to have had trouble with the rest. So I'm going to ask you to pause your movie for a little bit now and try again to solve the problem. Okay, well, continuing now with the solution, we want to know the equation for velocity. This would be part D. Well, the equation for velocity is v equals u plus at. So is just really get the parts. U is -5 meters per second, and the acceleration is 2 meters per second squared. So v equals -5 plus 2t. Then part E is when will the particle pass by the origin of the reference frame? Well, the origin of the reference frame is the coordinate equals to 0, x equals to 0. So the only thing you need to do is just get your position equation, 6 minus 5t plus t squared, set this to 0, and then you just solve the quadratic equation, which in this case here would be t1 is 2 seconds. Oops. T1 is 2 seconds and T2 is 3 seconds, meaning that the particle passes by this position equals to 0 twice. Now, when will the particle reverse direction of motion? Let me just explain this in here for part F. To reverse direction of motion, you see that my particle needs to be coming one way, it needs to be moving in one direction, it needs to momentarily stop, and then it turns around and comes back. So reverse direction of motion implies that the velocity must be momentarily 0 and must go from positive to negative or negative to positive. So to find this, I'm just going to get the equation for velocity that we have, -5 plus 2t, and I want to set this equation to be 0. And this is going to give me a time of 2.5 seconds. That would be my reverse direction of motion. Now let's go for the three graphs. I want the position, velocity, and acceleration graphs. The simplest graph of all is going to be my acceleration graph. So that's the graph I should start. So acceleration in meters per second squared versus time in seconds. And to do that, I am going to get here a very nice straight line. And my acceleration, we checked before, is 2 meters per second squared. So I'm basically going to have this here, okay? A horizontal line in 2 meters per second squared. My velocity starts at -5 meters per second. So it's going to start at -5 meters per second. The slope of the velocity graph, let's remember the slope, or how the IB call gradient, is the acceleration. And because I have an acceleration that is positive, this graph here for velocity is going to have a positive acceleration. Positive slope, my bad. Oops, wrong key. And the positive slope then is going to be something like this here. This intersection here is the moment when the particle reverses direction of motion. And we have already calculated that this happens at 2.5 seconds. So then this would be a velocity versus time graph. Finally, now let's prepare here a position versus time graph. The initial position of my particle is 6 meters. Because my velocity is initially negative, I should have initial negative slope. So velocity is negative from t equals 0 to t equals 2.5 seconds. Okay, but this velocity is approaching 0. So notice this. If I do my velocity, my position graph, concave down, this means a speeding up graph. If I do it concave up, this is going to mean now a slowing down. And let's remember that from 0 to 2.5 seconds, we have negative velocity, but positive acceleration. That means it's slowing down. So my graph must be concave up. So basically, what I'm going to have is this here. From 0 to 2.5 seconds, oops, not a good line. From 0 to 2.5 seconds, our particle is going to be slowing down, and this is going to be 2 seconds. Now, after 2.5 seconds, now I have velocity positive and acceleration also positive. So now my object is speeding up, and I should now have something like this here. And this is the other 3 seconds. And my graph, of course, is completely out of scale. Well, I'm going to ask you guys now to solve problem example 7, which is just a repetition of example 6, just another equation, one more example for you guys to get more practice. So x equals 32 plus 4t minus 2t squared. Please pause the movie for a little bit, try to solve the problem, and then come and check my solution. Okay, then going forward with our solution, we have here the general equation of this problem. X equals 32 plus 4t minus 2t squared. And the general equation for the constant acceleration motion is x equals x naught plus ut plus 1/2 of a t squared. So for part A, we're going to have basically x naught is 32 meters. For part B, u is 4 meters per second. And for part C, 1/2 of the acceleration equals -2. So the acceleration is going to be -4 meters per second squared. If by any chance at this point you had made any mistake, I'm going to ask you to pause the movie again and then try your solutions to check and come back here to watch my solution. Okay, moving forward with my solution, the equation for velocity, which is on part D, v equals u plus at, is now at this point just grab the numbers in. So u is 4 meters per second, and the acceleration is going to be -4 meters per second squared. Part E is asking now for the particle passing by the origin of the reference frame, and the origin is just coordinate x equals 0. So we're just going to get the equation 32 plus 4t minus 2t squared and set this to 0. I solved this before actually showing you my solutions, and I found t1 to be about -3.1 seconds and t2 to be about 5.1 seconds. And we just cannot accept a negative answer for time, because since the initial time is always 0, okay, since my initial time is 0 a negative time will represent something moving backwards, and that does not happen. So we just don't accept this one, and then my answer is 5.1 seconds, meaning the particle only passes by that 0 point once. And then the final answer here, the final question is when it's going to reverse direction of motion. So let's remember that reverse direction of motion, velocity must be 0. So I'm just going to get my equation for velocity, 4 minus 4t. I'm going to set this to 0, and then this is going to happen at t equals 1 second. So here is my reverse direction of motion. Finally, we have the graphs. I should always start by the simplest possible graph. So I'm going to start by my acceleration graph, acceleration in meters per second squared versus time in seconds. And that acceleration is going to be negative 4 meters per second squared. So I'm going to have here a negative 4 and basically a horizontal line, always constant here. Next graph is going to be my velocity in meters per second versus time in seconds. And then my velocity graph will start at my initial velocity 4. And basically, because I have here a negative acceleration, my velocity graph should have a negative slope as well. So I'm going to have a graph that basically is doing this. This intercept here, the horizontal intercept, remember, is the point where you will reverse direction of motion. And we have already calculated this happens at 1 second. Finally, my position graph, x in meters versus time in seconds. My position graph will start at 32. Because my velocity is initially positive, my graph will start going up, but this velocity is approaching 0. So I need to have a graph that is going to be concave down and is going to reach a 0 point. So basically my graph must do something like this. After this velocity equals 0, 1 second, now I'm going to have a negative velocity and I'm going to just go speeding up and speeding up like this here. This intercept we calculated a minute ago and is going to be 5.1 seconds. Okay, moving forward with our problem solutions here, let's go to my example number 8, which is draw the corresponding graphs. So position and velocity and acceleration graphs. Okay, so here is the first example. This is my second example. And then third example. I'm going to ask you all to consider that my velocity is initially 0 here. And that velocity initially 0 here. Okay, and let's assume that this graph here is a parabola. Okay, so let's just make this assumption. I'm going to ask you guys right now to pause the video, try to solve the problem on your own, and then come back and follow my solution. Okay, so you have already checked, hopefully you have already tried the graphs. And then let's see here what we get for example 8. My velocity is a straight line starting at initial velocity 0. So my position graph should start at some point, but should start horizontal because my initial velocity was 0. And because this now is going to be increasing, is going to be becoming faster and faster, my position graph should be somehow a concave curve like this. A straight line velocity graph implies constant slope or constant gradient, and that means then a constant acceleration. And so that would be my constant acceleration motion, and it must be positive because I have a positive slope. Okay, so I have here a slope that is positive and constant. The second part, my graph is the graph of a parabola. So this here is curving up, means my position should still start horizontal at some point. This initial position is really not determined. You just make it any point you want. And it should curve up. But because the velocity is going to be speeding up, this position graph should actually curve up even faster than before. And then my acceleration graph is no longer going to be constant because I don't have a constant slope in here. Well, because this is getting steeper and steeper, my acceleration graph should then be also increasing. So something more like this here. The ones who are doing calc would realize that if this is a parabola, then my acceleration should be a straight line, although that was not really a requirement for this problem. Finally, my last example, okay, velocity changes its behavior at a certain point here. So initially my velocity is increasing, then becomes constant. My position graph should start increasing, should start concave up, and at some point should become a straight line. So roughly this point here is when I change behavior. My acceleration graph should start as a constant horizontal and at some point should drop to 0, because here now I have constant velocity, and constant velocity implies acceleration equals to 0. Moving to the next example, example 9, you guys have now position versus time graphs and are asked to draw the corresponding velocity versus time graphs and acceleration versus time graphs. So let's again just assume here that, well, you know what, those assumptions are not really important. I'm going to ask you to now pause the video and try to solve it on your own, and then you come back and watch my solutions. Well, I hope you guys have already reached a solution. So now let's move on with my solution here. My position graph is that of a straight line, always increasing. That means then that I have a constant slope, and constant slope will imply for me a constant velocity. So I'm going to have here a constant velocity. Because this graph, oops, that's not really a good constant graph. Let's erase and do it again. Okay, that was a little bit better. And because this was a positive slope, because this here was also a positive slope, that means positive velocity. Now if the velocity is constant, acceleration is going to be 0 all the time. So this is going to be 0 like this here. For the second graph, I did not say anything, I'm sorry, but let's assume that this here is a parabola, and it starts here basically horizontal. So being a parabola means that my velocity graph should be linear, starting at 0 and performing this way here. And if my velocity graph is a straight line, meaning that I have constant acceleration motion, then my acceleration should be constant like this here. And positive because I have in here a positive slope. Finally, the last one is going to be my position is moving in a straight line up to this point here, and then after that the particle basically just stops. So this here is particle at rest, and this here is particle moving at a constant velocity. So my velocity graph will actually be constant for a while, and after some time is going to come down to 0. My acceleration graph is going to be 0, not defined at this disconnection here of the velocity, at the kink on the position graph, and then 0 again. And this will conclude this problem here. Well, we are pretty much done with the problems on my set of notes. Example 10 is going to be a homework for you. Okay, so please do this as a homework. We're going to discuss next class. And example 11 is also a homework for you. We're going to discuss next class. remember, to better solve examples 10 and 11, that drawing a picture of your problem is a good idea. So basically, in here, we're going to have the lane, okay? The speeder is driving at 40 meters per second, and the trooper will take off 1 second afterwards. So if this here is the trooper, okay, the speeder passes by the trooper, and 1 second later, when the speeder is here, moving at 40 meters per second, then the trooper will start pursuing with an acceleration of 4 meters per second squared. The first thing you need to do is figure out where the speeder is when the trooper takes off. And after that, you can then set the equation for the speeder, the equation for the trooper, and you just then need to see what happens when they are side by side. Example 11 is a little bit more challenging, has a little trick in there, is more for students who are really into more challenging math problems. We're going to discuss this next class.